Okay, guys, so we're going to talk about volumes. Now, this is actually one of the more, for me at least, interesting uses for integration because when it comes to like two-dimensional objects, area is definitely an important aspect, but more importantly, I feel than area is going to be volume because while we can certainly like approximate shapes with regular shapes, so such as like a soda can with a cylinder. The reality is, if you look at a soda can, it isn't actually exactly cylindrical. It's kind of like got this top that does this, right? So you can certainly approximate a cylinder like this, um, but it's never going to be exact. And we often care about exacts, at least to a certain degree. And so using a cylinder, while that's decent, isn't perfect. And so that's the reality of a lot of three-dimensional shapes is that we can have things that are maybe generally shaped similarly, but if we want to find the actual volume of an object, then we need to go to integration for that, not just our geometry. But that doesn't mean that we can't use integration for our basic geometry as well. So essentially, we have like this intuitive concept of what volume means, but to actually find it in a precise way, we have to use calculus to find some basic exact definition of volume. And there's actually a couple ways that we can do that, and we'll talk about them. Um, the first one we're going to talk about is kind of thinking about them as slices. And that's actually, in general, how I think about kind of generic shapes. When I'm dealing with three-dimensional objects in geometry, what I think about is that all 3D shapes, for the most part, follow a face that's been extended over its height. So in this case, this shape right here, this cylinder, it has this like half circle or elliptical, whatever shape as a face. And so if you find the area of this face and then drag it over the height, we'll get its volume. Same thing with a circular cylinder. If we find the area of its face and drag it over its height, we can find its volume. Same thing with a rectangular box. If we find the area of one of its faces, either this bottom, this top, the side, or what have you, and then drag it all the way through, we'll get a volume. Now, that concept can be carried through for a lot of different basic three-dimensional shapes. Cones follow similarly, not exactly, but the general idea is you find the base, in this case a circle, and drag it over the height. However, it um, uses like a 1/3 base times height, much like the triangle is 1/2 base times height, and three-dimensional triangular shapes tend to be 1/3 base times height. So it's not exactly the same, but it's similar enough. So the idea here is that when we have shapes in general, what we want to do is we want to integrate the area from A to B of its face. That's the general idea. So when it comes to a rectangle, if we integrate it from A to B, so its kind of height, and we integrate its face, then we'll find the volume. And that actually applies for more complicated shapes. Like here, if you notice, we have this red slice here. So we essentially break it into infinitely many slices of its face and then integrate it from A to B from the points we care about. Okay, so this is sometimes referred to as kind of um, like cross section method or like the um, like uh, what is it called? Sometimes we refer to it as slice method, disk method. That's the word I was looking for. So the disk method. The problem with the concept of the disk method is obviously this isn't a disk, but a lot of the shapes we deal with tend to be disk in shape, so we sometimes refer to it as a disk method. Anyway, the point is that essentially we're doing the same thing we do with basic shapes, which is find the area of a face, drag it over the height. The only difference here is that we want to find some face that works. So here we're doing it with relation to x because maybe this face is easier to describe in terms of a function. And that's the other difference, is that the area isn't like some uh, like definite number, some constant like it would be here. These are constant areas. This area would vary with respect to x. So depending on where we are, in this case it's pretty large, but down here it's going to be smaller, and down here it's going to be smaller. So it varies with respect to x. So we have to describe our area in terms of x if we are integrating with respect to x along the x-axis here from a to b. But in general, our basic shapes, or our shapes in general, are based around this. And we can use the same thing when it comes to integration of like our more basic cylinders or like rectangular prisms, is that it's just going to be the integral of the face's area. So it'd just be area times the difference from B to A, that is the height. So area times height. Now, when it comes to a more complicated shape like a sphere, for example, like how do we know that the volume of a sphere is 4/3 pi r cubed? Well, we can show it pretty easily with this method. So again, in this case, you notice this looks like a disk. This is why it's called the disk method. And so what we do is we essentially want to create a bunch of disks. So we slice this sphere up into a bunch of disks. Now, each one of these disks has some area that we're then going to integrate. So we want to integrate this from, in this case, negative r to r. And if we have it in this orientation, it doesn't actually matter because it's a sphere, it's the same either way. But based on this drawing, we're doing it along the x-axis. So we're going to describe it in terms of x. And so that means that we want to describe this function in terms of x's. Now, r is a constant, it's just some value. We're just doing it in generic, but we could say like, what if the r was 1, right? Or whatever, it doesn't really matter. But we're just gonna do it in generic for all spheres. Okay, so now the idea here is that we wanna describe the face of this circle in terms of like x's, okay? Now, if you think about this right here, the face here has a radius of this thing, not the radius of the sphere, but the radius of this red portion here is our y height, okay? So if you think about it, a circle, the equation of a circle is x squared plus y squared equals r squared. That's the generic equation of a circle. Okay, again, not the r of our sphere, but the r of this thing here. Okay, so essentially, we want to describe this sphere, which has a radius of y in terms of x. So we want to find the equation of the circle in terms of x. So that means we're going to have to solve for y. Okay, so if we solve for y, we are going to move the x squared over. We have y squared is equal to r squared minus x squared. Now that we are here, we can take the square root, and we get our y equation is the square root of r squared minus x squared. Okay, so this is our y. Now, if we want to find the area of this circle, area is pi r squared, right? So pi r squared, that's the area of a circle. Now our r in this circle is y. So we're gonna, or excuse me, not the area, our radius of our circle here is y. So we're gonna plug our y in for r here to find the area of this face. Area is pi r, r is square root r squared minus x squared, squared. Again, our radius of our circle here is y. Okay, so that square root then gets taken care of. We're left with area is pi times r squared minus x squared. So this is the area of our face in terms of x's, and we're going to plug it in and integrate because, again, the generic form of volume is the integral from the bounds of the area. So pi r squared minus pi x squared. I'm just going to distribute that pi into both. Okay, so we're going to go ahead and integrate this thing. The integral with respect to x of pi r squared, again, r isn't a variable, it's a value like 1 or 3 or 10 or square root, whatever, it doesn't matter. It's just some value, okay? So this is a constant here. So the integral of a constant is just going to be pi r squared x minus, in this case, pi x cubed over 3. And we're going to do this from r to negative r, because again, we're doing it over this whole thing. Now, there's also other ways to deal with this. I'll talk about that once we're done with this. If we plug in r here, this is going to be pi r cubed minus pi thirds r cubed minus, now this negative r, so that's going to be a negative pi r cubed. A negative and a negative makes a positive pi thirds r cubed. Okay, so distributing this negative in, we have pi r cubed plus pi r cubed is 2 pi r cubed. We have negative pi thirds minus pi thirds is minus 2 pi thirds r cubed. Now these are like terms, so we can combine them. This would be like a 6 over 3, this 2, so this is like a 6 over 3 pi r cubed minus 2 pi over 3 r cubed. So 6 minus 2 is 4 pi thirds r cubed. That is our volume as we expected. So one of the things to note is that what we're doing is we're creating this disk, but this disk, and the reason why it's often referred to as a disk, this face here, this area is a circle, and this area of a circle is pi r squared. So if we can describe our circle in terms of whatever variable we're dealing with, in this case x, that's going to make it so that we can actually find volume by integrating the face with respect to whatever value we're doing, x or y, depending on the situation. Okay, so again, it's always going to be the same basic concept. Find the area in terms of x or y, whatever's easier, and then integrate it with respect to those axes. Now, a few things to note is that if we have a sphere here, or really any kind of shape that is symmetrical, we didn't really have to integrate it from negative r to r. We could have integrated it from 0 to r and then just doubled it, which if you're lazy like I am, I tend to do. So real quick, the integral is still the same. The only difference is this portion here, is that if we took pi r squared x minus pi x cubed over 3 from r to 0, and then just like doubled it, then that should also end up with the same thing. So let's double check. So 2 times pi r cubed minus pi r cubed over 3 minus, plugging in 0 here, we just get a 0. We end up with this thing here, 2 pi r cubed minus 2 pi thirds r cubed, which we already know is 4 pi thirds r cubed. So again, you know, if we want to make our integration easier for certain situations, sometimes it's better to restrict the bound from 0 to r, but technically speaking, we're doing it from negative r to r. I just did it the easy half and then doubled it. That just helps me avoid potential mistakes with like negatives and stuff. So I tend to do stuff like that. All right. So again, the idea here, regardless, is we're essentially thinking about it as like solids of revolution. So essentially what we're doing, and that's what we did here, is that we think about a single like height value here in terms of x. So we're solving for y in terms of x, and then we're revolving around the axes that we're integrating with respect to and creating this like solid. So here we have this gumdrop shape. Now it is varying with respect to x, okay? So if we are going to talk about like something like this and we want to find the volume of this gumdrop, right? We want to describe the area of any particular face. So here we have this y equals square root x graph from 0 to 1, and we're creating a face. And this face has an area, and that face's shape is circular. So we want to find this radius of this little face, which is our y value. It's the height, and our y is the square root of x. So we want to find our radius, which is y, but we want it in terms of x, so square root x, because we are clearly integrating along the x-axis. Okay, so what we do here is we're going to take the integral along our x-axis from 0 to 1, and so that means it's a dx, and now we're going to find the area. So again, area in terms of x. Now, what is the area? The area is a circle again. Area is pi r squared, but our r is y, or square root x. So area is pi square root x squared. So that means that the equation of our area, in this case, is pi x. So this is what we integrate with respect to x from 0 to 1. The integral from 0 to 1 of pi x dx is going to give us pi x squared over 2 from 1 to 0. Plugging in 1, we get pi halves minus plugging in 0, 0. So the volume of this gumdrop is pi halves units, maybe inches, let's say inches cubed or whatever. Okay, so again, it's just a matter of finding the face. And when we refer to this as the disk method, they are disks, they're circles, but not everything has to be circles, as we'll get to in a bit. It's just a lot of them tend to be circles, but we're restricted then to things that have kind of circular cross sections. But we're not, this concept is not restricted to only circular cross sections. It's just that circular cross sections are easier, so that's why we're starting there. But the reality is it's always just cross sections dragged over the axis that we care about. Okay, so let's do another one. Again, so let's say we find the volume of the solid obtained by rotating the region bounded by y equals x cubed, y equals 8, and x equals 0 about the y-axis. Okay, so we're creating this shaded region here around the y-axis now. So we're going to integrate from 0 to 8. That's the height. So the integral from 0 to 8. And so that's along the y-axis. So we're going to do dy. So that means that we want our area in terms of y. Okay, so let's now talk about the face that's generated when we make this circle. If you see, we have this 3D object. And again, when we rotate this thing around the y-axis, we create this circle here. And so this circle here gives us some width, which is its radius. And that radius here is the x value at that particular point. So here's the x value at that point, here's the x value at that point, and so on and so forth. That's how wide the radius is, or that's what the radius of this circle is, okay? So again, we're going to now describe this x in terms of y. So we have the equation y equals x cubed. And we want to describe this function, but in terms of x's, because this is an x, and, or excuse me, we want to solve for x in terms of y, because we are integrating with respect to y, and this value here is x. So we have y equals x cubed. So what is x in terms of y? Well, we take the cubed root of it. So x equals the cubed root of y. This now tells us what x is in terms of y, which is good because we're going to use that because we want the area in terms of y. So again, area is pi r squared. Our radius of this circle is x. Our x is the cubed root of y. So we're going to plug that in for r. So again, a is pi x squared, but instead of x, we're going to go with function in terms of y, because that's what we're integrating with respect to. Pi cube root of y squared. So that is to say, area is pi times y to the 2/3. All right, so this is the area of any cross-section. Plug it in, integrate it. Integral from 0 to 8 of pi y to the 2/3 dy. Again, area from 0 to 8. And we're doing it with respect to y because that's easier. Okay, so again, we're just taking whatever's easiest. So in this case, doing it from like, from -x to x wouldn't really work because x varies. We don't have some restriction. We could maybe say we're integrating until here, find what this is along the x-axis. That would certainly work, but then we'd have to describe the height in some way, and it's just hard. So instead, we're doing it in terms of the easier one, y. Okay, so the integral of pi y to the 2/3 is going to be pi y to the, we're adding 3 to that, so 5/3 over 5/3 from 8 to 0. So that means that we're going to have 3/5 times pi times y to the 5/3 from 8 to 0. So that means we're going to have 3 pi over 5, 8 to the 5/3 minus plugging in 0. That would just be a 0. So we'll go over to Desmos real quick to see this. Okay. So 3/5 times 8 to the 5/3 is going to give us some value, 96 over 5. So that is 96 over 5 pi. And again, cube units or what have you, whatever units we're talking about. All right, so again, that's just the basic concept. We just need to describe the radius of our circle in terms of either x's or y's, depending on what we're integrating. Find the area of that circle, then in terms of that variable, integrate that area. That's the idea every time. Okay. Now, let's talk about what happens when we create a shape through like a mixture of two things. So in this case, we have some region enclosed by the curves y equals x and y equals x squared. And let's say we want to rotate it about the x-axis. So we create this shape here. It's kind of like a wine glass, or I guess a martini glass, I should say. But the inside curve has a curve to it. So rather than being straight like the outside edges, the inside has this like curve to it formed here. And essentially the idea is we're still taking slices, but you'll notice that our slices are no longer circles. They are kind of like washers. We refer to them as kind of like a washer shape. But the idea here is still the same. We have essentially two circles that are created. We have the outside circle, this one here, okay, and it has a radius. And to find the area of this shaded region, we take the area of the big circle and subtract the area of the little circle to just get this region in between them. So when we're dealing with, more complex three-dimensional objects that form hollow insides here, well, that just means that we have to find the area of the outer minus the area of the inner, and do the same thing. Found the face area, integrate it along this axis, okay? So if you notice, this is from x is 0 to x is 1. That's what we're going to integrate this from. So this is 0, this is 1, okay? So we're going to integrate this from 0 to 1. We know it's going to be dx because it's along the x-axis and our bounds of integration are x's. So that tells me that I need to find the area here in terms of x. So again, I always start with, okay, what does the area need to be in terms of? All right, so let's now talk about the outer circle right here, this outer circle. So the outer circle is formed via the y equals x graph here, okay, this thing here. So if you think about it, as we rotate this around, the radius of this circle here, this line and this line are the same here. The radius of that is the height, the y of this, which is x. Y equals x, okay? So that tells me then that area is pi r squared. Our r is y or x, doesn't matter. We want it in terms of x, so we're going to do x squared. So that's the area of the outer circle. Now let's talk about the area of the inner circle, okay? It has a radius as well. In this case, let's just go off of it over here, okay? This is the radius of that circle right there. It is the height as well. That means it's y. But our y is x squared, and we want to describe our radius, our y here, in terms of x's, so we're going to describe it as x squared. So area is pi r squared. Our r is y, but again, we want it in terms of x's, so that would be x squared squared. So we have our area of our outer, our area of our inner. To find the area between them, we subtract them. So we'll go ahead and do that. So the area of our washer here is pi x squared minus pi x to the fourth. This is the area of our washer. Okay. All right. So again, that is what we're dealing with in this problem, is creating this area, but it's just the two areas of the two circles that we created, subtracting them. Okay, so let's go ahead and plug this area into our integral. The integral from 0 to 1 of pi x squared minus pi x to the fourth. Now you might think, ooh, x to the fourth is bigger than an x to the third, x squared, so wouldn't that make that negative somehow? Does that make any sense? Well, yeah, if our bounds weren't between 0 and 1, you'd be right, but a fraction taken to a higher power is smaller than a fraction taken to a lower power. It's only like numbers greater than 1 that get bigger as we square them. If they're fractions, then they get smaller as we raise them to exponents. So this would be the smaller number, so that makes sense. So we're integrating these things with respect to x. So the integral of pi x squared would be pi x cubed over 3 minus pi x to the fifth over 5. And we're going to do this from 1 to 0. Nice and simple. 1, I like these ones. Pi thirds minus pi fifths minus 0. So pi thirds minus pi fifths, that would essentially be a 5/15 and a 3/15. That would be a 2/15 pi. All right, so that is our volume. Okay, so again, same idea. We find the face. In this case, our face is just a more complicated shape. It's just a washer instead of a circle. But a washer is made up of two circles subtracting each other. All right, let's do another one. This time, let's rotate the same problem, but across the y-axis. All right, so let me go to Desmos here. I've had pictures already created, right? So I actually pulled those from the book because they have good pictures. I find that initially when you're first doing these, it's nice to have pictures, so it's like more, it's easier to understand. The idea here is the same though, okay? When you have to do it yourself, you still want to have a graph. Okay, so when I'm working on these things, if I don't graph it, that's just going to make my life miserable. Okay, so we're going to take this region here and we're going to rotate it around the y-axis now. So again, this point here is 1, 1. This point here is 0, 0. So we're rotating it around the y-axis. So we essentially create like a more of a wine glass shape instead of a martini glass, but the inside has this sharp edge. Okay, that's what we're creating. I'm going to get rid of my horrible drawing because it will probably just muddy it up a little bit. But the idea here is the same. We create this region, and we're rotating it around the y-axis. So we have this, and if you think about it, the radius of each of these circles is creating this kind of washer effect again. But now the exterior function is our y equals x squared, and the inside function here is y equals x graph. Okay, so we're integrating this from 0 to 1 along, because this is along the y-axis now. So we're going to integrate it from 0 to 1, but with respect to y. It just so happens that their intersections 1, 1 and 0, 0 are the same x or same y, 1 and 1. So we're going to do this with respect to y now. So that means that we need to find the areas in terms of y. So again, outer circle, I'll do it in the same colors. Let's just erase this and do it with the circles, with the colors that I used. So the outside here is blue. This is our y squared. Okay, if you think about it, the radius of this thing is the x. Okay, so this would be x. Now, if we take a look at the inner circle here, its radius, that wasn't very centered, huh? Its radius is also x. Okay, now we want it in terms of y though. So let's start with the red one because that's easy. Y equals x. They're the same, okay? But let's talk about y equals x squared here. So our x squared, our x, we need to solve for x here in this equation. So y equals x squared. How do we solve for x? We take the square root. Now, the plus or minus would matter if we didn't square areas anyway, so it doesn't really matter. So we end up with x equals the square root of y. So that's our radius here. This is our radius here, y. So talking about the big circle, the area of the big circle would be pi r, but again, our r is square root y squared. And our little circle, the area is pi r, but our r here is y squared. Okay, so taking a look at this, we'd have pi y minus, because we're going to take the big circle and subtract the little circle, pi y squared. And again, same thing, the power being bigger on the small one makes sense because we're looking between 0 and 1, so we're less than 1 here for most of it. Okay. So this is the area of our washer in terms of y. So pi y minus pi y squared dy is what we're going to integrate. So we have pi y squared over 2 minus pi y cubed over 3 from 1 to 0. Okay, plugging in our 1, we get pi halves minus pi thirds. So minus 0. Same thing as before, this would be like a 3 over 3, and this would be a 2 over 2. So 3 minus 2 is going to be pi over 6. And that would be our volume of this object that we created. So depending on what we revolve it around, changes what the actual volume would be of this solid. Our previous one was 2/15 pi, and this one here is pi 6. Okay, so it's still talking about the same region, but when we rotate it, it creates different solids. Okay, so we can do this around any axis that we want, is the point here, but we can also restrict this to like anything else. We don't have to do it with axes. Much like our areas, we don't have to do volumes around an axis. We can do it around some other thing. So here, we're going to do the exact same solid we've been dealing with, but now we're going to revolve it around a line y equals 2. So again, it's still the same general shape. Initially, it's still the same 2D shape, but we're revolving it now around y equals 2. So thinking about this thing here, again, same equations. We have some disk that we're creating, but the concept is still the same. We have an exterior and an interior that's being created here. The exterior line here, the height of this exterior, if you think about it, the exterior here is y equals x squared, is the line that is the exterior shell here or whatever, okay? The interior is our y equals x graph. Those are the two things we're dealing with, so let me use the same colors here. Okay, so if you think about it, when we revolve this, we're still creating two circles. Okay, this is the outer, this is the inner circle. So we need to think though, what would the radius of this circle be? So in this case, the radius is from 2 down to this point here. Okay, now let's think about this. This is a height of 2 overall, but then it subtracts off this height here. This height is the y. This height is the rest of it. So 2 minus y would give us that height. Again, this is 2. This is y. 2 minus y would give us this distance right here. So that's what we're going to describe as our radius. It is 2 minus y. Okay, now we're going to do the same thing with the other one. It's the same concept. This is 2 overall. This is the y value of that. So 2 minus y will give us this region, the radius. 2 minus y. But we are integrating this along the x-axis from 0 to 1. So that means we're integrating from 0 to 1 dx. So we need these 2 minus y radiuses in terms of x's. So let's go ahead and do that. Again, what is y? Well, in our purple, we would have 2 minus x squared instead of 2 minus y. And for our red, we'd write this as 2 minus, well, y is x, so x. So those are the radiuses that of our two circles that we're creating. So let's find their areas. Area of the purple one would be pi times 2 minus x squared squared. And in our other one, area is pi r squared. Again, our r here is 2 minus x squared. Okay, so we are going to subtract those two areas. So let's go ahead and clean this up. This would be pi times 4 minus 4x squared plus x to the fourth minus pi times 4 minus 4x plus x squared. Okay, so all right, so this pi is in everything. This is kind of the area that we're talking about here, this area here. Now we could clean this up a little bit. I'll probably do that. Let's just pull the pi out first. Then that would be 4 minus 4. Those cancel. Okay, then we have a negative 4x, but it's turned into a positive, so it's going to be a 4x. We have an x squared. That's going to be a negative x squared, and a negative 4x squared is going to be negative 5x squared. An x to the fourth, that's all we have, so plus x to the fourth. Okay, so again, double checking this. That's a negative, that's a positive, that's a negative. So 4 minus 4 is gone. Negative 4x squared minus x squared is negative 5x squared. And we have our x to the fourth. Okay, so just wanted to double check that. So this is our area in terms of x. So this is what we are going to integrate. So plug this into our integral here. The integral from 0 to 1. Again, it's from, we're doing it along this x-axis here from 0 to 1. Okay, so the integral from 0 to 1 of 4 pi x minus 5 pi x squared plus pi x to the fourth, I'm just taking care of it now, dx. Okay, so that would be 4 pi x squared over 2 minus 5 pi x cubed over 3 plus pi x to the fifth over 5. And we're doing this from 1 to 0. So plugging in 1, we have 2 pi minus 5 pi thirds plus pi fifths minus 0. So I'm just going to do that on Desmos real quick, not subject you to my horrible arithmetic in my head. So 2 minus 5 thirds plus 1/5 gives us 8/15 pi. Okay, so again, we can rotate this around anything. The big thing is, again, thinking, what is the radius of our circle? It's the height here of this line up to 2, taking out the height of our outer function here. Okay. Now, a few things to note also, I haven't mentioned this, but like I obviously set it up where the outer is minusing the inner. But if you accidentally mixed up what's the outer and what's the inner, it's still probably going to work out. You'll probably just get a negative. And so you should just be aware that if you see a negative, you probably set it up the wrong way. But that's just something to be aware of. Okay. Let's do one more rotation. In this case, we're taking the same function, but now we're going to rotate it about the line x equals -1. Okay, so same idea as before. We're thinking, in this case, we're creating this shape. We have an outer and an inner. Okay, the outer radius here is based on our y equals x squared. Okay, so this is our y equals x squared graph here. This inner function 1 is here, and this is our y equals x graph here. Okay, now if we think about this, if we're rotating around the -1, okay, that would mean that we have this is -1 right here. Or really, if we're thinking in terms of distance, it has a distance of 1. Okay, then the rest of the distance here is just the x. And the same thing over here, the rest of this distance here is just x, the x width, okay? So we're going to integrate this from 0 to 1 again. But this is along the y-axis, so we're going to do a dy. So we need to describe our area here in terms of y. Right now we have them in terms of x, the radiuses. It's 1 plus x and 1 plus x, okay? So our radius in general is 1 plus x, but for each of these inner and outer equations, we have to consider them in terms of that. So we have our outer function. Let's start with the outer function. It is y equals x squared, but we need it in terms of just x, so we can plug it into our radius function here. So solving for x, we would have x is equal to the square root of y. So the radius of the outside circle, let's again go to a picture side on. This one here, the radius is 1 plus x, but instead of x, we're going to say square root y. Then the inner function, the inner circle, again, terrible drawing, I know, is 1 plus x as well, but instead of x, it's our function y equals x. So it's 1 plus y. So these are the radiuses of our two circles that we're going to subtract them. So we're going to subtract their areas. So our area of our outer is pi 1 plus square root y squared, pi r squared, minus the inner, pi times r, 1 plus y squared. Okay, so doing a bit of math here, we have pi times 1 plus 2 square roots y plus y minus pi times 1 plus 2y plus y squared. Okay, so cleaning this up a little bit, 1 minus 1 will go away. Okay. Y minus 2y is going to be pi, so negative negative y. Okay. And then we have our plus 2 pi square roots y. And then we have our minus y squared pi. Just distributing that pi into it while we're doing it. So this is my area. Let's double check it. Ones are gone. Square root 2 square roots y is by itself. Y minus 2y is negative y. And then we have our y squared. Okay. So this is our area in terms of y, which again is what we want to integrate. So we're integrating from 0 to 1 of our negative pi y plus 2 pi y to the 1/2 minus pi y squared dy. Okay, so if we integrate this, we'll have negative pi y squared over 2 plus 2 pi y to the 3/2 over 3/2 minus pi y cubed over 3 from 1 to 0. Okay, so plugging in 1 here, we have negative pi halves plus 2/3 times 2 pi minus pi thirds, and then plugging in 0, we'd have minus 0. Okay, so let's see, cleaning this up a bit, negative pi halves plus 4 pi over 3 minus pi thirds. Okay, let's go to Desmos here. Negative 1/2 plus 4/3 minus 1/3 is 1/2. So pi over 2. All right. So again, it doesn't really matter how we rotate this, whether we rotate it around the x or the y-axis or some x value or some y value. The concept is still the same. We are creating, in this case, washers, but we're creating circles that are being rotated, and we need to find the radius in terms of whatever variable we're integrating over. So again, we're taking it from 0 to 1, the height of this bowl that we created essentially. Okay, and so we need to think again, what is the radius of these bowls? In this case, 1. And then the x, and 1 and the x here. Okay, so the idea is the same regardless though. Find the area, integrate the area. That's all. Now, this can extend beyond circular shapes that we create. So if we have something like this, these are when we start talking about just finding volume using our cross-sectional areas. Again, we've been doing that. Our cross sections have been areas of circles, but the shapes aren't always circular. So in this case, we're not generating it through some revolution. Instead, we have some shape that's created via other shapes. So the idea is still the same though. We want to find the area of a face. So find the face that's the easiest to describe if we were to slice this up. So if we're thinking about this one here, these are rectangular in shape. Each one of these faces along this is a rectangle. And so if we find the area of the rectangle and then drag it across this whole way, then we will find the volume of this shape. So let's go ahead and see that in action. So the base of a solid is a circular disc. So this base here is circular. Okay, so the face here on the bottom is a circle, but if you notice as we go up, by the time we get to here, it's just like a line almost, but it would just be like a rectangular shape. So obviously we're not going to drag it over the height because this can't be described in terms of a circle over the whole height. It's only a circle initially, and as it goes on, it stops being a circle. Okay. but we at least have that. It has a radius of 3. Okay. Parallel cross sections that are perpendicular to the base are squares. So that is to say, these cross sections are parallel to each other as seen in the picture, and they're not just rectangles, they're squares. So they're really specific. Okay, so we have a square being made here, and same thing here. This is also a square. Okay, so it looks like we're going to take it in relation to this square face here, these squares here. We don't want to take it in relation to here, this way, going this way, because obviously it's not squares this way. So that wouldn't work. In fact, the cross section going this way looks kind of like maybe this, like it has a bit of a curve to it. Now you could maybe potentially describe it as like a semicircle and like a rectangle or something if that was necessary, but this face is just squares, so that's going to be really easy. So let's think, what is the area of a square? Well, that would be kind of like the height times the width, right? Width times height in this orientation, okay? So what we need to do is we need to describe this, but the nice thing is that it's a square, so it's rectangular. Rectangular in general would be width times height, but for us, it would be just width squared, or just height squared. Because it's square, it's width and height, they're the same. So either one would be appropriate. Now, this is a circle, right? So we're taking it in relation to like from here to here. This is what we want to integrate this thing. If this is a radius of 3, then kind of like this point here is like, let's talk about it in terms of an x and y. It doesn't matter what is our x and what is our y. Like which axis is x and which axis is y. Does it frickin' matter? No, it doesn't, right? Who cares? We can just set it up. Let's just call this y. And then this would be x, okay? Again, it doesn't matter, but I think that would, in the way I'm visualizing it, that's how the axis would look to me. But again, it doesn't matter. I arbitrarily choose which one's my x and y because, it's 3-dimensional. It doesn't actually matter, and it's symmetrical here anyway. So that means that we're going to be integrating it along my y in this orientation. So I'm going to integrate this along y. We could also, because it's a circle, like we don't want to integrate it with respect to x, even though we could maybe do that from -3 to 3 as well. The problem is that if we do that, then we'd have to be going off of these faces, and these faces look like this. So we want to do it along this axis where the faces are squares. Okay, so we're going to do it from -3 to 3. But this is a circle. So technically speaking, if I wanted, I could do it from 0 to 3 and just double it. That would also work. Either one, though, doesn't matter. So we'll see. All right, so now what we want to do is we want to find the area of the faces and describe them in terms of y. Okay, so because again, we're integrating this with respect to y. Now, if we think about this thing here, okay, what is the width of this rectangle? Well, it's the x distance. Okay, right here, this is x distance, but it's 2 of them. So our width can be described as 2x's. Okay, now, what in the world is the x value here? Because again, we want it in terms of y. So it's not the y, right? Clearly it's not the y. But what function is creating this edge that these are touching? Well, this function here is a circle with radius 3. So that is to say, x squared plus y squared equals 3 forms this circular shape. Okay, this shape here, the function line that this is touching, is forming x squared plus y squared equals 3 squared. Sorry, I should have done 3 squared. Okay, so this is the equation of our line that our width is kind of going out to touch. So it's the x on this. So we need to solve for x on this function and find it for our width. So let's go ahead and do that. Solving for x, we're going to have x squared is equal to 9 minus y squared. Taking the square root, x is the square root of 9 minus y squared. When we take the square root, we need a plus or minus, but it will work itself out. Because again, we're talking in terms of strictly positive here, because that's this one, and then the negative is going to be the other side, the double. Okay, so our width then is 2 times x, but x in terms of y is, so the width of our rectangle is going to be 2 times the square root of 9 minus y squared. And we know that the area of a square would be the width times the width. So that is 2 times the square root of 9 minus y squared, width times width, or width times height, because the height is the width, it's a square. So that means the area of our face in terms of y would be 4 times 9 minus y squared. That is to say, area is 36 minus 4y squared. That is the area of any particular face here as our y goes on. So we are going to integrate this area, 36 minus 4y squared. And I'm going to take it from 0 to 3 and then double it, but I'll also do it the other way just to show that they are the same, because again, it's a circle, so I can get away with stuff like this. And I'm super lazy, so the integrals on zeros are much easier for me. Anyway, integral 36 would be 36x minus 4y, I'm sorry, I'm doing it with respect to y. So 36y minus 4y cubed over 3 from 3 to 0, and we just like kind of double this. So let's just see. Plugging in 3 into this, well, I can't do that in my head necessarily. 3 times 36 minus 4 times 3 cubed all over 3. All right. So we have 72. So this is 2 times 72. Also plugging in 0, that's just zeros. So 2 times 72 is 144. Okay, so that is the area here. Now let's double check that Andy didn't do something wrong with this by doing it from -3 to 3. Just because again, that's technically what's happening, okay, in my drawing, where I set the center at the origin. That's just easier to describe this as the center at the origin. So if we take this from -3 to 3, again, this is 36y minus 4y cubed over 3 from 3 to -3. So the 3 was 72, to say that's what we got in the first one. And -3, that would be minus a negative 3 times 70, 3 times 36 is 108, -108 minus a negative, so that'd be plus 4 times 3 squared, because 3 cubed over 3 is 3 squared. So 4 times 9 is 36. I'll just write it that way. Okay, so real quick. So 108 minus 36, that's going to be a -72 here. This is -72. So we have 72 plus 72, which is 144. Same thing as we got in the other. Okay, now I chose the origin to be in the center because I can easily describe this circle here then, right? But we didn't have to set it at the origin. What would have happened if we set the origin here? What if the origin was here? Well, then we'd have to describe this circle in terms of that origin. So that would be, first of all, x squared plus y squared equals 3 squared, 9 here. This is a circle of radius 3. But what if we want to shift it up where the base would be on the origin? Well, that would mean we'd have to do something like change the y. So this would be y minus, I think, 3 squared. Let's see. I'd have to mess around with it a little bit, but yeah, that did it. So this shifted it up 3. So now we'd be integrating from 0 to 6 of this function here, using this function to describe our x's. So like we could certainly do that, but using this was a little bit more challenging, but we could certainly do it from 0 to 6 if we wanted. Okay. We just have to use a different function if we change the origin. So we choose the origin to be somewhere easy rather than this one. We want to use this because it's a nice simple function. But again, we could certainly have used this one to describe our x's. Solving for x here would have been, so just a real quick thing. We could have integrated, so again, it's, if we solve for x here, x squared is 9 minus y minus 3 squared. So that means x is the square root of 9 minus y minus 3 squared. This could have been our x, and then we would have like squared it. So we could have taken the integral from 0 to 6 of this, like 2 times the square root of 9 minus y minus 3 squared if we had wanted dy. Like this would have been fine too. It would get you the same value. But let's just actually do that real fast on Wolfram. Let's just see if it gives us the same value. So if we integrate from 0 to 6 of this thing here, so this would be 4 times 9 minus y minus 3 squared, that dy. See what we end up with. 144 as well. So again, if we change the bounds of integration to 0 to 6 for this circle, we still end up with the same volume. All right, so that is kind of our cross-sectional thing, okay? Now, let's do another one. The base of the solid region is enclosed by the parabola y equals 1 minus x squared and the x-axis. Cross sections perpendicular to the y-axis are squares. Find the volume of the solid. All right, so let's go ahead and take a look at this graph first of all. That way we can at least think about the face here. Y equals 1 minus x squared. Okay, so here's our face. And we want to do it and the x-axis. So essentially it's just here from this point up. So it's this little thing here. So that's the base that forms this. Now cross sections perpendicular to the y-axis. So that is to say, let's go ahead and do this. Okay, so cross sections along this value here. Let's shrink this down just a little bit. Okay, so the cross sections along the y-axis, like these, are squares. So what we're creating, if we're looking on, is squares along this shape here. Okay, so we have like squares along this thing. So in this case, this is my y-axis, this is my x-axis. Let me let's just try and do that a little bit better. How about that? Okay, so I will draw this as best I can. Three-dimensional, I'm not super great at, and I'm not super great at two-dimensional. I'm just not good at drawing. Okay, that's simple as that, right? So the function we're dealing with here is this thing, okay? And then cross sections with it, I'm gonna go ahead and draw in like, I don't know, blue or something. So I'll look like this, and we're dragging it along. So the next one would be a little bit smaller. Okay. But it's also further out, so freak, I don't know. Dang you, perspective. Anyway, you get the idea, maybe. Anyway, so we're taking this along that. Okay, so the idea here is that same thing as before, we have some like face that we're creating. And those faces along the y-axis, again, this is y, this is our x, okay? That is going to be along the y-axis, so we're going to integrate from 0 to 1 dy. So we at least know that. Again, I always start there. Now, let's talk about the face that we're creating. It's an area y. Now, the area of our face, our cross sections, are rectangles. Okay, and again, same thing as before. If you think about this width here would be like the x, and this width here is also an x. So that means the width, which is the height, is 2x. Now, our x is the distance out to this function that's touching it. Okay, so initially it's like 1, but it's changing with respect to this function here. This function is y equals 1 minus x squared. So we need to solve for x to find our function in terms of y. So we need to solve for x. So real quick, y minus 1, or y equals 1 minus x squared. If I add the x squared, subtract the y, I get x squared is equal to 1 minus y. Take the square root, x is equal to the square root of 1 minus y. This is how wide each of these things are. Square root 1 minus y. And there's two of them to find the width or the height. And so the area of a rectangle is width times height. So it's going to be 2x squared. So again, area is width times height. So that means area is 2x times 2x. So in our case, in terms of y, area is 4 times 1 minus y squared square root, which is just area is 4 times 1 minus y. So that means our area of our rectangle face is 4 minus 4y. This is the area of any particular face with respect to y. We're going to integrate it. The integral from 0 to 1 of 4 minus 4y dy is going to give us, we've been doing a lot of 0 to 1s mostly because it just makes my math easier, but we can do it from anything. We get 4y minus 4y squared over 2 from 1 to 0. So plugging in our 1, we have 4 minus 2 minus 0. So that would be 2. And that is our volume. Okay, so again, this is the integral here. When we're doing volumes, oftentimes it's easiest to think about cross-sectional areas and integrate it.